Okay, I'm back. This is William, and so last video was kind of me talking for a while about historical swerve drives that we've seen in FRC. I find that stuff really interesting, just watching progression, but you don't, you're in luck because you're gonna sort of get into technical details um, of what makes swerve drives today tick. Um, so I mean, I want to sort of pan over to a module, but I think the page I'm on is going to really shed some light on how a lot of things work. So if you watched the last video, or if you don't watch the last video, that's okay. Or if, ideally you have some knowledge of how server modules work. But if you don't, um, I'm assuming that at least you know that there are there are mounted at each corner, and there are two motors, usually one driving the rotation of the wheel and one rotating the entire module. On the rotation of the wheel, you don't need more than a normal radial bearing to take the load of the rotating wheel, because all the load experienced there is axial, so it's weight on the um, axle, and if you have a bearing that can take that load, that way then your wheel will spin fine. Right. What you're worried about is load on the rotation of the module itself. So as you turn sideways or you rotate or whatever, you are scrubbing against the carpet, so there's some frictive force uh, exerted, not axially, but uh, sort of uh, torsionally. So instead of weight that a radial bearing can sort of counteract with correct load ratings, if you threw a radial bearing into a lot of the thrust and torsional bearing loads that you see in servo modules, they would fail. So you have to pick the thrust bearing mechanisms carefully. And a lot of things will work. You just need to pick something that works for you. And also, when I say works for you, it has to work for your application. So what I'm looking at right now are these Kadon really slim open bearings, or just the really slim bearings. And the type here is the X 4-point contact. So there are two key things. They're slim, they're really thin bearings, and they have 4-point contacts. What a 4-point contact bearing does is it takes the load both radially and thrust load. So it takes the load of just like weight on the rotation of an axis, as well as loads perpendicular to that axis, the thrust load. Moment load, I actually don't really know what it is. Something that I should look into later. It takes all of those, where a radial bearing would typically only take load. And there's a image somewhere of what an X contact bearing does. Um, Here, so yeah, turning two bearings into one. So let's start here. So this is a normal radial bearing. So there are two tangent curves, and the ball bearing sort of is rested on both points, and it takes that load radially. On an angular contact bearing, it's I, I don't know how this works exactly, but I'm assuming. Oh, I guess so. This way, it takes load going straight up and down, so there's weight bearing or radial bearing. And here on the angular contact bearing, it takes side loads. And here on the X contact, the 4-point contact bearing, it takes loads. So, it sort of replaces any combination of these bearings with just one. And you sort of see that here. So typically, you'd use needle bearings or angular contact bearings or yeah, you use copper bushings or sets of bearings to take the load of a Swerve module as it's rotating. But teams have managed to reduce that complexity with these X contact bearings. You can see here, they take a lot of. So most popular probably is the KA035. 035 stands for 3.5-inch inner diameter, and the outer bore is 4-inch. So it's a very thin section, only a 1/4 inch in thickness. They're able to take a lot of load. So while moving, they take more shock loads than I would ever expect a drivetrain to take in a match. I think the loads a drivetrain takes, they do get up there. I would never expect them to hit this. Even for the thinnest bearing, a 2-inch bore bearing, I think these are pretty well within sort of the load that you expect a robot to take. Plus, you have to consider that there are 4 of these in each robot. So your setup, and even though you're only ever gonna target a subset of these bearings, you still get a combination of thrust loading capability from these bearings. So I think you're set up for success with these. And sort of where you can see this visualize is something like the Swerve Drive Specialties setup, which they use the one I just pointed out, the KA035 HPO. It's not, they don't have the KA part because they get their bearings from China. So I mean, Kadon or whatever, Swerve Drive Specialties, they all get their bearings from the same manufacturer in China. It's just that one gets shipped to them for $20 per bearing, and one gets sent to Kadon, who resells them for upwards of $200 per bearing. $200 per bearing. So again, it's not proprietary, it's OEM stuff, so it's all fair game, but there's a significant price advantage to not using American made here. So this is the setup, and they have load bearing set up here, and so any side loads this way, this way, this way, this way, all that load is dispersed onto this bearing, which is kind of cleverly held in from the top and bottom by these bolt heads, pulley on top. And that load, that load is taken by the bearing instead of the parts, the components in the actual Swerve module. So the pulley isn't being damaged, the legs aren't being damaged, the gears aren't being damaged, the radial bearings inside here, which are not equipped to take that load, are not being damaged. Even worse, and even more importantly, you're not damaging the motors. If it turns out that you cannot take the load, like the load bearings, the thrust bearing setup, and when I say bearing, there's like it's very confusing terminology. Very confusing terminology because the mechanism is bearing the load, but you're literally using bearings. So I just hope you can parse through that on your own. But the thrust bearing setup, or using these X contact bearings, is really key in that, because if you can't take the load, and it means that the force is distributed into the system, and so there's more torque required to turn the gearbox than you would initially think, right? You think that, okay, all I need to turn is the robot's weight, and I can assume that I'll be able to spin, counting for friction, some X amount of weight. Maybe a quarter of the robot's weight. I need to be rotating on the spot. However, if it turns out that whatever thrust load bearing setup you have set up isn't actually equipped to take the thrust force of spinning the modules, and you're going to end up pulling more current to your motor, to your turn motor, to drive the gearbox, to turn the whole system. What can happen then is you can burn out your motors, you can stop turning, you can stop moving on the field, and then you can have a whole system failure. Or if you can't move on the field, then you can't play. It's the same deal on the drive motor, but that isn't so much of an issue. In recent years, like not immediately recent, but in the past 2-3 years, teams did start switching to 775 pros for the drive motors. That's when people started seeing some drive issues. But really, the key is to build robustly. So before we hop into anything, I'm going to start Notepad 5. This is visible. It won't be. I think there's sort of a priorities list when you're building any drivetrain. So this is agnostic to Swerve drive, tank drive, Mecanum drive, H drive, any combination of drives. The very first thing is it has to be robust. Okay, I'm going to type in capitals so that you can see this, but I doubt that you can actually read it. It has to be robust. It has to withstand the vigors of however long your robot competes. It has to work 100% of the time. If your drivetrain is having issues, then you can't do anything else in the game. Right, so that's something that you hear repeated a lot, and it's very true. The drivetrain has to work. With robustness being your #1 priority, you have to work from there. No matter what, this drivetrain has to work. But after it works, like, what do you want? And these go light in hand, but you want to be lightweight and compact. So once you ensure that the drivetrain works, you're going to say, okay, how can I take this package, however big or however small, and how can I make it even smaller, as small as possible, and fit in as small of a box as possible so that I can build over and around it. And this is like the driving philosophy around like West Coast drives. A lot of teams ran non-cantilevered drivetrains because they thought that their drivetrains needed to support, and California teams decided that, hey, we're gonna push the limits of how robust this drivetrain is. Take out the parallel plate. We're gonna push the wheels out more, and we're going to see if that will give us, and we'll see how well that works. And it'll end up working really, really well. And what that does is it gives teams that run that configuration of West Coast Drive the ability to build more inside. You have more space for the electronics board. You have more space for mounting mechanisms, and more importantly, you have a wider working width for your intake. Right, that's a key thing. Being able to intake as wide of a span as possible. And also in recent years, it's also like the elevator. The more width you give to your elevator, the more space you can have in a final carriage, allowing you to potentially even have like a pass-through mechanism. And you can see teams like 254 in their 2018 robot really leveraging their West Coast Drive, enabling them to build such a wide elevator. And of course, you can build a wide elevator on a non-West Coast Drive robot. It just makes it harder for you because then you either have to mount higher and get less travel, and then maybe have to add more stages, which decreases your width, or you have to figure out a way to mount low, but also squeeze a lot of space in a not wide space. So that's a more recent example. I don't have a file to show you, but you should just search it up. Look at 254's 2018 robot. The very impressive robot, won the world championship, and their pass-through mechanism is something that worked really, really well and inspired a lot of teams in 2019. So lightweight and compact are the few key things. I'm actually going to, I kind of went over compact instead of lightweight, but I think lightweight I didn't really cover, but I think it should make sense that it kind of goes hand in hand, but it's also more important. An average Swerve drive today weighs fewer than 30 pounds. Tank drives for the past 10 years have weighed 30 pounds around, and teams that really push its limits get it down to maybe 20 pounds or even later. So even today, Swerve drives are in the upper end of weight, of like heaviness for drivetrains. 5, 6, 7 years ago, and 15 years ago wasn't even a question. Swerve drives weighed a lot. So you just do the math in your head. The swerve drive specialties gearbox, they weigh 5 pounds each, everything fully assembled. I'm not going to count motor controllers, even though they do weigh some significant amount. You multiply this by 4, so that's 20 pounds for all 4 modules, and then box tubing and a belly pan to keep everything together rigidly. You're looking at 30 pounds. A tank drive, similarly, you get your gearboxes down to 3.5 pounds, maybe 4 pounds each. So that's an 8-pound gearbox, box tubing and everything, plus a belly pan, and maybe like 14, 15 pounds. Add in all the wheels, you can get around 20 pounds. So a fully optimized tank drive, which is very achievable for many teams, is already going to be 5 to 10 pounds lighter than like the most optimized swerve drive we're looking at. I mean, there are right now even more custom, better optimized solutions out there that weigh even less than this. But assuming that the swerve drive specialties, the 2910 Mark II swerve drive is the benchmark for top swerve drives, and we know that there's already, even at this point, kind of a weight gap between like tank drives and swerve drives. But if you take it back like 5 years before, like swerve drive modules weighed 10 pounds each or 11 pounds each. You can point to it here. I think I still have it up, which is the Rev 2 modules. This weighed a lot. Yeah, so this Rev module, which, if you look at it, doesn't look too different from things I've showed you before. You have a drive motor, and reduction, and that goes down. Sprocket reduction goes down to the bevel, gear to gear reduction, wheel. That drives the wheel. Rotation module goes from this bag motor, versus planetary reduction, this offset plate, drive the rotation to a different sprocket, which drives this whole chamber. This is your copper bushing setup. This turns the whole module. So, the same thing that's been happening for decades at this point. But there are enough optimizations across every single step here. They take this from 11 pounds to 5 pounds. You can see here, probably they don't use chain. They don't use any chain. They use fewer gears. They use less plate, way less plate. They use lighter motors. Oh, are there 2-sim motors here? Okay, that explains it. Okay, there are 2-sim motors here. If you took off one of them, you'd get it down to a 9-pound module. Okay, so let's say we don't use 2-sim motors. That's ridiculous. What the hell? I didn't even notice that, but that makes no sense to me. So yeah, you take off that other sim motor, so you're looking at 9 pounds now. The sim motor weighs 2.2 pounds, a full kilogram. So let's look at, again, this is 5 pounds versus 9.2. Compare. That is 4 times 5 pounds, 20 pounds. Whereas the Rev 2 from like 10 years ago, and so when you don't use two sim motors per is 4 times 9 pounds equals 36 pounds. Right, so it's 16 pounds extra. You add on your belly pan and whatever. So you're looking at 25 pounds, which is like pushing 40, 45 pounds of drivetrain. That extra 20 pounds is like 20% of your robot. So oftentimes, what happened 10 years ago was that if you were running Swerve Drive, you were making major cuts somewhere else in your road. You were making things less robust, or you were like spending significant brain time and manpower trying to figure out how to make your mechanisms super light, right? Because it was either make your mechanisms as light as possible or make major sacrifices in how you assemble your mechanisms. And if you somehow had everything figured out and you could get everything you want, robust and perfect, then you had to put in a significant engineering effort to get it to all fit together. Whereas with tank drive teams, they have this weight envelope. They can operate knowing that they can add stuff in and leave things unpocketed, but still come out with a robot that makes the weight, makes the 120 pounds or 125 or whatever weight they set per year. So in the 10 years that have progressed since what I would consider like the benchmark best module to what is now the benchmark best module out there, the biggest gain is going to be in 16 pounds. The key thing is that no one module is more or less robust. Though, considering my own personal experience with the copper bushing setup in Rev Pro 2 module for the turn, I think the cross sectional. Again, I haven't run this before, so I had nothing but anecdotal experience. But from what I've seen, that these work really really well for taking thrust load. The copper bushes, which is like their purpose is to take slow rotation, high thrust loads. They have not held up. They have not held up as well for. But again, it's a flawed comparison because I've run those 4 years now and they've failed twice. Whereas I've run these 0 times and they've failed me 0 times as well. So that whole section was sort of about the bearings, but so after we have robust and lightweight and compact, this is an inline. So after compact, you really want it to be serviceable, like easy to maintain and swap in and out. Before even serviceable, no, I said serviceable. Serviceable is really, you care more about your end product than you do about what's coming next, which is easy to manufacture. So easy to manufacture it or COTS uses so in competitions, if your module fails or you want to replace a bolt or just small stuff from either like placing out a worn bolt or changing out an encoder to oh my god, the entire leg fell off, or oh my god, the bevel gear is just absolutely wrecked, every tooth is stripped, things that you can't foresee, to just minor things. You want to be able to fix your drivetrain really really easily, because in between matches you have in the playoffs you have at best maybe 6 to 10 minutes to repair your drivetrain. In the qualifications, if you're in a district, you really have no turnaround. And if you're in a regional, you have slightly more headroom. But even then, you want your drivetrain to be serviceable so that you can easily fix everything else on the road. You don't want any one part to hog you up. Especially your drivetrain, you do not want that to be taking up your time. So it being serviceable in a competition is very key, I think, after the 3 kind of core components. And I think a lot of times you will see teams trade off serviceable for a compact and lightweight because they think that being able to fix your modules, if something beyond control happens to them, that you have to be able to repair them immediately. Right? Like, you build your module to be as robust as possible, and then you also build it so that you can easily fix things. And I think that these sort of get there, and they get to the ease of changing out a wheel is pretty high. It's like a West Coast drive in that you can take out a bolt and the wheel will kind of just fall off. With the bevel gear attached, of course, so you have to take off the bevel gear and put it. But it's pretty drop in, which is a good thing. And after serviceable, it has to be easy to make and use or use COT solutions. And this is where we're sort of diverging from what I think a lot of people can generally consider like pretty true to what I consider pretty true. So I think a lot of people would agree with me up to this point. I think at this point, you get to see sort of the divergence in um, high capacity, wealthier teams and teams that don't quite have the same capabilities. The reason why teams buy modules, COTS modules like this, SDS module, is that it contains a lot of like billet pieces, machine plate that you cannot make it at house. I would say like the biggest uses of these are probably the billet wheel. So the wheel assembly is not a custom wheel. It's a really, really like lightweight, but also like very compact wheel that you apply your own tread to. And the tour de force, I would say, is this pulley. So it's a HDD 5mm pulley, but it has a modified profile where it only has I can't count how many teeth it has, but it has a reduced number count of teeth for like a very big pulley. So they have like emulated the profile of a 5mm HDD pulley, but only keep the teeth every like 5 or so teeth. And this enables for still like pretty precise tracking of the rotation, but um, makes it very easy to machine out of aluminum. So they have a mill that makes all these passes. It's just it comes out a big round stock of aluminum, and it comes out like this. It comes in a big round stock of aluminum, and it comes out like this. And for a lot of teams, they don't have first like the CNC mill to do this, and then second the design chops to do this, and third like the CNC operating ability to run a program and confidently pump these out, 4 at a time, perfectly machined within a build season. And that's what this module does is it gives you all those things along with like the nicely machined plate, which I would say is more in reach for plurality of teams. It gives you these nicely machined plates as well, along with the custom bevel gear, which again I haven't even gone to. This custom bevel gear is big as well. This you can't really buy unless you get it from China, which is a huge like leap. Or like some I think maybe the Thrifty Bot has started selling these bevel gears for cheaper, but you still have to modify them for this custom drill pattern. Yeah. So you have to buy these bevel gears usually from China, another supplier, and then you have to again mount them to a CNC machine, probably a mill or a router, and get this hole pattern drilled into it. So it comes as a fully there's material here, and there's not a hex bore or any 1 7/8 inch drill pattern, hole pattern. It's just stock, and you have to empty it out, bore it out, and drill these holes. So there's a lot of things happening behind the scenes that goes in this module that just gets handed to you when you buy it. I guess like the biggest thing is like this bearing. Unless you want to go on AliExpress and coordinate with multiple vendors who don't speak perfect English, and you get to figure out how to get the best price across however many vendors. Unless you want to do that, then you have to buy these bearings from these guys, from from SDS. Either that, or just this year, this vendor called the Thrifty Bot started selling these for $20 each, which is not as prohibitive as the $200 you'd have to pay if you bought them in America. And these from SDS, I think they come maybe $30 each, so they're not cheap, they're not expensive, but they come at a cost. So there are a lot of really nice things happening in this module before we even get into like the actual design specifics. There's just things happening here that make it tick that you, as a normal team, could not really produce normally. So either whatever sword type you make has to be easy to make, or you can just buy it. You can just buy this module, or it can be some combination of the two. And I think the last point priority is price. So at the end of the day, you have the $5,000 cap on how much you can spend on your robot, bill of materials. So you don't want your drivetrain taking up too much of that, because while most teams will never hit that $5,000 cap, you can come close to it, or you can even end up over it. And I will say most of the teams that end up over it or get really close to it are teams that run Swerve Drive, because Swerve Drive, custom or not, is very expensive. Take a look at it. If you can pull over the Swerve Drive specialties page, their modules run, let's say, standard kit, everything, at $400 each, and you need to get 4 of these. So that's $1,600 for a full kit. That is a lot. A tank drive gets up there, but maybe like if you buy all cots and you buy custom gearboxes and everything, it'll run you maybe $800. And if you build a custom gearbox, you can get down to $500 really, really easily. If you reuse parts, you spend like less than $200 on a drivetrain every year. If you're reusing tubing and you're reusing your gearboxes, I guess you can't do that if you have a custom gearbox. But even then, if you're just remachining plates, all you're doing is paying for the cost of aluminum. That's in a tank drive. Here, you can reuse if you buy a COTS kit, then great, you can reuse the COTS kit every single year. If you use a custom kit, you have to remachine a lot of pretty hard to make things, usually, unless you design intelligently. But every single year, there's a higher buy-in cost for this Swerve drive. Right? Either you're using an old design and you have to remachine some parts that are harder to make than they are for a tank drive, or you're buying for the first time a COT solution or machining for yourself a brand new Swerve drive. And that will always be harder to do and more expensive to make than doing your own custom tank drive. And if you just think beyond the bill of materials right now, you have to consider that a team does not have unlimited funds. Like there are some teams that do have, for all intents and purposes, unlimited funds, but a lot of teams just are not in that price range. You have to just consider every year is okay. Yeah, we can afford these Swerve drive modules, but are they? Is the learning investment worth it? Is the competitive advantage worth it? And is the complexity and time investment required to make these work worth it? And that has to be accounted for. Yeah, and those are the 6 main levels of the 6 main priorities I have in any drivetrain. This is seventh and final one is it has to be cool. There's not much to say about this. At the end of the day, you're building a robot that plays a game, and you want it to do the game and play the game really well. And for all of your mechanisms, you want them to perform well. Just like any other mechanism, you want your Swerve drive to work well. Often, like nowadays, making it look cool, making it do cool things is all happening in software, but mechanically, you can do a lot of things to make it. Like I think this custom billet pulley is cool. The fact that they actually get away with not using a fully profiled pulley and make it out of aluminum is really cool. I think the bevel beside gear is really cool to lower the profile, and I think the symmetrical design is really cool. I think not having to think about mirrored plates or anything or changing how you assemble things is really cool. So I think mechanically there's still a lot of cool things you can do, but we're not going to go into stuff beyond that. At this point, I would say Swerve drives are a very mature field. There are always lots of optimizations you can have, but I consider a mature field when like something you buy off the shelf is as good as something you can make in house. And that's a good point to start at. So I've been looking at the Swerve Drive Specialties module a lot. We're gonna kind of, again, same as before, breeze through past. I don't want to bore you too much because I'm not trying to like give you a history lesson. I'm just trying to go through like where things failed and how to improve from there. So this is the Rev Pro 2 module, and this is where a lot of teams started, my team included. And I'm going to show you a custom design later too that I whipped up earlier this week that still relies on these core geometries. So this isn't the whole plate, but it shows all the cool stuff really. It's the I call this the leg or the drive column. It's a column that, so here you can see there's a copper bushing here, the steering assembly. So this sprocket, the sprocket gets attached to this whole pattern. This fits through the tube, and this is the thrust bushing. This is the hip that connects down from the two connecting tubes, and also attaches to the rest of the legs. So this is like a really thin. I never actually. Okay, that makes sense. Okay, I've never actually looked too deeply through these modules. My team used them when I was a freshman, and I never really got too much of a chance to see what's going on. But I think here's a lot of really cool things. It's very compact, and also like it's all squeezed together. This big portion could be made a lot smaller if you didn't fit it through the tube, and you get even like maybe another inch or two of clearance. And this is like the thinnest possible load bearing solution is just a thin copper bushing, right? It's a ring of copper. So thinner than the thrust bearings, the X contact bearings that we saw earlier, and if they worked, they would be really good. But in my experience, they did not work as well. They didn't work as consistently as we to. My team would like to. This compresses the whole thing together, and here is the magic where the sprocket attaches to this hub, this bolt circle, and then on this this is not what I want. Is this it? This is the piece that holds together the whole drive column, and this is the other side of this. Sandwiching everything together, there's or the bottom of the bushing. So there's two lids, I would say, that compress the bushing together and hold the whole thing together. Bottom and the top. Bottom goes through all the way through to the top of the bore of this. That's where the sprocket gets mounted to. So there's a whole series of compressions happening that squeeze the whole module together. Very elegant. From there, I think it's pretty. I would say it's pretty standard. There's bevel gear to bevel gear, one-to-one transfer, final gear to gear. It's a very small wheel. It's very little clearance, but as you say, clearance is clearance. And the coolest thing is, you think, hey, there's no support here. Won't this whole system sort of be really susceptible to side loads? Like, won't this middle bend? And you think, yeah, but no. There's, whoops. This assembly, this bottom shaft is a standoff holding together. So it's a dead axle. This will work now. There are two bolts holding it in place, and the shaft, the dead axle shaft of the wheel, is also serving as a standoff to support the load of everything. And I think that's really elegant. That allows you to keep everything thin, so you don't have to sweep out as big of a circle. Yeah, it keeps things lightweight. And when I say sweep out, it's sweeping out a smaller circle. There's a concept that viewing from the bottom, even though this hip is like, let's say 63.5 millimeters, I don't know what that translates to in inches. Yeah, no, I don't know. Even though it's this width, it really takes up the space of the circumference of this 3¼ inch wheel, because it rotates around, it sweeps out a circle with diameter of 3¼ inches. And you can play with it, but usually you're limited by that factor. That however thin or small it gets up to here, you have to account for space at the bottom for the wheel to move freely. And I think with the more modern directions, you're gonna see how teams get. Okay. I have lost Swerve pulled up, but I'm not going to go through them too much. This is Team 16's Swerve Drive module from 2016. I'm not really sure what I can go through with this. I just thought they're a really cool team. They've been running Swerve Drive for a while, and I forgot to mention them, or rather, I didn't mention them in the other video, and I didn't want to snub them here. Team 16 is a team from Arkansas, I think, and they have run really cool Swerve Drives every single year. They've recently made the switch to a lot more 3D printed stuff with, the rise of robust pieces that you can kind of just whip out immediately with the first printers. And before that, I knew them because they use slip rings really. They really leverage slip rings to the most in FFC, in that they didn't use a coaxial reduction for their drive motors. They attach their drive motors to the turn. The way they do that is that in order to get around the wire wrap issue that prevented you from rotating continuously, they had a stationary slip ring which transmitted power to the motor without needing to run wires without needing to run a finite length of wires from power source to the motor. So here, power was continuously transmitted to the motor without needing to run a length of wire. Rather, you can run a length of wire, but that power was continuously transmitted as it rotated. Yeah, that's it. So there you have less weight. You run less weight, and there's less mechanical complexity, but then you're relying on the electrical complexity and robustness of the slip ring, which for a team like that, I'm sure it worked out. I don't know if they still run the system or not. I don't know how much this weighed, but just from like a ground like viewing, I don't think it took a very small space, and I also don't think it was very optimized in terms of like compactness, but it was what served them well, and they were a very high performing team. So I take nothing against them. I'm not. I just want to show this to you. I think it's a cool example because of its non-coaxial motor setup, but still continuous rotation configuration. So that's all there is to take away from it. This model is incomplete, so I don't even know how their thrust pushing, thrust bearing is set up. An important thing to note is that this is from 2016. So in 2016, there were very, very big obstacles to run over. So that kind of explains why it's not super compact, because you had to have a big wheel that could traverse big obstacles. Like, for example, this is what our Swerve drives look like. So very few teams did this, but we were one of those stupid, but cool teams that ran Swerve in 16, and we not only ran big wheels, but we ran pneumatic wheels. So they're air-filled tires that compress and can easily drive over obstacles. So it shows of how Swerve Drive can adapt to any game. Is it always the wisest choice to run Swerve Drive in a game that's very punishing to it? I would say no. I think we cracked these pulleys once or twice, but never game breaking. Surprisingly, this was our most robust Swerve Drive ever. I think because we knew that it would be very hard to do it. We put special effort into making sure that it would work really, really well. And you can see here how this is so 2013 was actually our first year doing Swerve Drive, but we don't talk about that here. And by we, I mean Team 3419. It's a team I was in high school. All these Swerve Drives are just from that time. Team I mentor, so 395, who I mentor right now, has never run a Swerve Drive. Maybe we'll do it for the off season. So this Swerve Drive was our second year ever after running a Swerve successfully in 2015. And in 2015, beyond sort of assembly, we use basically off-the-shelf Revolution Pro 2 modules. And you can see how we adapted those modules for this year, 2016. The leg, instead of being made of 3 plates, was a billet. And which else was, if it was a, no, it was definitely billet. Okay. So it was a big block. It wasn't even box tube, I'm pretty sure. It was a big piece of aluminum bored out to accommodate this wheel. And it was very thin. So I think you're going to see this deviation a lot, going from conversions from Revolution Pro 2 modules to like that design family to sort of the modern bevel beside wheel modules from Swerve Specialties and West Coast Products. This module was very long, pretty thin. It was still 5 inches wide, which is a lot by standards today, but for the game, it was thin. It was a fairly compact module width-wise, and this allowed us to have a wider intake, more working space. But again, not that much, not that much that's like really blowing our minds right now. It's the same copper bushing setup, slightly different column, and for the turn, there's a 1-to-1 reduction from the gearbox to turn, and the drive is just a straight pulley reduction. And the key thing to note here is that there's a 1-to-1 encoder position here. So there's a huge planetary reduction here, and there's a integrated CTRE mag encoder stage in the first planetary gearbox. And from that output portion, there's no further gear reductions on the turn. So that way, whatever rotation we're measuring at that last position on the SRX is true to the actual position on. And so that's the benefit of having a 1-to-1 setup, where you know that once you have your absolute position calibrated, you know from whatever reading you read off that final encoder stage, you know exactly where the module is relative to everything. Any other sort of ratio will lead to, besides some like funky math, will lead to readings where like if you're reading, let's say 180 degrees, you can either be at 0 or 360. Right? It can lead to places where you end up with a duplicate where you don't know how to turn. That's not good. And you can overcome that with like absolute positioning and everything. But if you have to recalibrate your position every single match, that's not a place you want to be. Like that is something you can do, but I consider it a bad idea. This is 2017. This is a different variation Swerve drive. This is from 2767 World Champions in 2017 and 2018. This is what they call the Third Coast drive. Same deal as what we've seen with the SDS and 1323 Swerve drives, where it's bevel beside wheel. I'm not going to note anything particular besides that it's 2 wheels. So it's a very fat module, but still thin on top. So it's kind of combining the Revolution Pro 2 design philosophies with a variation here to get it lowered to the ground. So instead of having to run a bevel and then a gear on that shaft and another gear, they run a straight bevel to bevel reduction. And this worked for 2017 because you had no need to clear the ground. It was a fully flat field, so you could run your gears or whatever as close to the ground as possible. And here's our solution for that here. So this is a really cool module, but it was also very heavy. So this is probably one of the thinnest modules I've seen around. It from side to side is 3 3/4 of an inch, and lengthwise it's pretty long. But that was a decision that we were okay with. So it's 10 3/4 inch long and 3 7/4 inch wide, and it swept out a slightly bigger circle than that, just 4-inch wheels. Again, very similar to the Rev Pro 2 modules. What makes it cool is that, whoops. Oh, you're missing here. What makes it cool is that there is a shifting gearbox. So you're familiar with shifting gearboxes in tank drives, and it's no different for a Swerve drive. If you want to shift gears, you engage a different set of dogs to do a different speed. And that was really all there is to it. But it wasn't often done because it was like tacking on complexity to an already very complex system. So it's not something that was done a lot. Made for a super compact system. This was I think really big step forward for us because we went from a fully caught solution to very custom solution, but for a game that wasn't well suited to it in 2016, and then in 2017 a game that was like neutral for both Swerve and Tank Drive. We really busted out our design chops and tried to create the best solution for it. And I think it worked out for us. The actual shifting gearbox, I'm not sure we actually use that much. But we had full court sprints and also very tight, precise adjustments, and that's where that made the most. Where we went really fast to go from where we scored to where we loaded, and then low gear, get the precise alignments, and also get past defense. This is what that looked like all in one. So here in that game, you scored these big, like oversized gears, and you wanted a huge space in the middle to be able to put our system, which intake gears and score gears right in here. And in that game, we chose not to shoot. Again, I'm kind of glossing over the game here, but there are two things you can shoot: wiffle balls, 5-inch wiffle balls, and these very big gears. And we said, okay, we're not going to worry about the wiffle balls too much, and we're going to dedicate our entire robot to scoring these gears. You can look through the game for your own rationale of how to do things, but this is how we chose to do things. So we made for much of that, it could be as long as it wanted to, as long as they didn't hit each other, and we just need to give as much space in the middle to the gears. And this is what that whole robot looked like. We wanted to give all that space to the gears, and they get what they asked for. I'm not gonna go over the robot, but it shows that we made a design decision to give as much space, to allot as much space to these gears, and it got that and even more headroom than necessary. You know that a lot of teams that picked up gears from the floor, because you had the option of either picking up from the floor or picking up from a station, did not have a what I call like a flipper system where it had these little prongs that held in a gear. They just had a roller intake, most roller intakes we see today, and reasons that I'm not going to go into, we did not pursue that path. We needed to have all this clearance instead of just like a simple like roller intake here to pick up the gear. And to pick up the gear. So this clearance was necessary. This space was all necessary, and we wound up having more space than even needed beyond that. That was really good for us. This was necessary for us. Although, if we were to do it all over again, we probably would not use this whole system. I'm not gonna go into it. 2018 is my last year on the team, and it's the final evolution of our gearbox. It's, I think, heavier, and it kind of just shows, it's just another maturation of the system. Where it doesn't use drifting gearbox anymore, but it's the same deal. It's lightweight, uses these 775 Pro motors. It still follows like the Rev 2 design family. You switched to pneumatic wheels because you wanted to go over the bumps in the middle. There's one big change here that I'm not going to get to go into. Actually, no, I have time to get into that. So going from 2017 to 2018, we still run this very thin copper bushing setup. Drive column assembly. All that load is being taken by this copper bushing. I'm going to show a short video of why that did not work. Do I have that? Anyways, what I was going to show you was a video, a very sad video for me personally, of us being dead on the field. Very important. Oh, here it is. So I'm team 3419, captains of the Blue Alliance. Volume of this. So there's autonomous. Our alliance members are doing whatever, and we are dead in the field. After this, we get knocked out. So this, what happened to me, was just devastating. Really, really sad for the whole team. Main culprit was this turn motor. Had burned out on the field. And the only reason we had for that was that, hey, this is the wrong way. This turn motor had burned out. This was not working. So we could not move our gearbox. We isolated the failure to this copper bushing. I said, okay, so this wasn't taking any load, and all of that was being exerted on our drive motor over here. And this motor, which we have spec'd out correctly for a properly working thrust bearing, was not spec'd out properly for a non-functioning thrust bearing. So we had thrust bushing. So because we failed to identify a failure mode here, we wound up burning out a motor and overall overtaxing the system, ending in a catastrophic failure. We said, okay, this is great, but how can we make sure this never happens again? So we sacrificed a lot of clearance and weight. Just to note, this whole system was pretty heavy already. This weighed 10 pounds per module, very heavy. This module barely got any lighter. It got heavier. So even though we lost the shifting gearbox and we made the plate slightly smaller, it weighed the same because of this drive column assembly. So we ditched the copper bushings, and as kind of forecasted in the KDON webpage, we stacked two bearings together. So in the column, we had two needle bearings set up, and needle bearings are tapered cones, and they're set up so they take both angular load and a little bit of radial load. And you need two of them stacked side to side to really create a nice full contact thrust bearing setup. Because just one is only going to take load in one direction. You want to have two angled points of contact against whatever clamping surface you have. So this whole thing added maybe another half pound of weight, but we said, okay, you know what? Our priority list goes that it has to be robust first and foremost. It doesn't matter if it's lightweight or compact if it doesn't work. So we said, okay, this has to work. How can we make it work? And this was the decision we went for. So despite losing all the shifting gearboxes and going from a sim motor to a 775 Pro, we only weighed in at 8.7 pounds. If we had kept this as a sim motor and kept our shifting gearbox, this would have been well over 11 pounds. And compared to the Rev Pro 2 module, this is actually worse because it's less compact and it's heavier. But it satisfies the key functionality of working. It's robust. And this was our chassis at the time. We barely made weight. This robot did not perform. So we've we're reaching an hour long on this video, so I'm gonna stop now. And we finally hit sort of modern Swerve drives and also what I've designed for this series, which is kind of a mashup between modern designs as well as my design history of Rev Pro 2 modules. I'm gonna cut it off here and we'll continue on